So our agenda for today, we got a couple of sections. We're going to talk about, really briefly, we're going to talk about what is CloudSearch. This is more of an advanced webinar, so I'm assuming most of you are familiar with it, but we'll give a quick review in case there are a couple of people that haven't seen it. We're going to talk about what location-based search is, and since that's based on distance, we're going to talk about computing distance. And then we'll talk about how you can implement that in CloudSearch, and then we'll take a look at a sample app that does location-based search. A little bit of housekeeping. You've got a space for questions over there in the meeting, in the GoToMeeting window. Feel free to type your questions at any time. We'll probably get to them at the end. And then this will be recorded. The recording will be on the AWS YouTube channel. We'll put the slides up on slideshare.net, and we will mail out a link to everyone. And if you haven't already, you can maximize your screen. I think it's in the upper left. There's a little button, and it'll make it a little bit easier to read some of the slides if you maximize that. All right, so straight on into it. What is CloudSearch? So CloudSearch is a fully managed search service. So it allows you to add search functionality to your application easily without having to be a search expert. It's very fast, and it's highly scalable. It's actually based on the A9 technology that drives the Amazon commercial retail site, so you've probably already used it. And it supports a number of features like faceting, synonyms, stop words, and customizing ranking. And that last one is important because it's actually the custom ranking functionality that we're going to use to implement location-based search. And to use CloudSearch is very simple. You'll go into the AWS console and hit Create a Domain under CloudSearch, and you'll set up a set of fields. You say this is a text field, this is a numeric field, title, author, things like that. And when you're done, you hit Create and go. You can also create things via the API or the command line tools, but most people start with the console. And then once your domain is created, you post your documents via HTTP, and you also search it via HTTP. There's a sample URL down below. You can see the domain -XYZ and region. Those depend on your domain. And then off of the end, you see Q = cat, and that's what you're querying for. So any language or tool that supports HTTP, you can paste that right into a browser, use it from Java, Python, Ruby, whatever you like. And then as you start to search, if your search traffic goes up, we will scale it up automatically. If your traffic goes back down, we'll scale you back down so you don't have to buy machines, rack machines, install operating systems, and all of those things. You just create the domain, put your data in it, and send us your search requests. And we take care of the rest. All right, there's your flying intro to CloudSearch. Now, for those of you that want more, our next webinar on the 17th will be a thorough getting started with Amazon CloudSearch. So you can go register for that one, and that way we'll talk you through the whole process of creating a search domain, configuring a search domain, how to get your documents in, how to run your searches. All right, but hopefully that gives you a little bit of orientation. We'll be talking about search domains. That's your set of data as we go. So now we're going to get into the meat of this one. What is location-based search? It's fundamentally just using your user's location and distance to various things as factors in your search results. All right? And key thing is, why are we talking so much about this these days? And people have always cared about what's the nearest restaurant, etc. But mobile is really the key driver because everyone's carrying smartphones now. And this means two things. One, they're moving to a lot of different locations and they're carrying their computer with, so they're searching from a lot of distinct locations. And the mobile provides the information as to location, so all of your applications can depend on having location information. So all of a sudden we're seeing a skyrocketing number of searches that are from mobile devices that are accompanied by location information. So there are any number of opportunities in this. You may hear the term SOLOMO, social local mobile. It's the big trendy thing for startups these days, is anything that has local characteristics, social characteristics, and is on a mobile device. There are all sorts of startups, probably several of you are in something like that. So we're caring more and more about location and distance. And then we're going to use the distance, and we may use the distance to say I only care about things within 10 miles of me, or you can say I want to see, I'm looking for a restaurant tonight on my phone, show me a list of restaurants sorted by closest to farthest away. And then the last bullet point here is the most sophisticated one, which is if I'm sitting here in downtown Palo Alto and I say, show me a restaurant, and there's one 10 feet away but it's a terrible restaurant, and there's one 20 feet away that's a great restaurant, you probably want to show the great restaurant first. So for a really good search application, you end up considering multiple factors like quality of the restaurant or whatever it is you're searching for, distance, text relevance. So you end up combining multiple factors, because the better your search results are, the more conversions you're going to get, whatever your goal is, more product you're going to sell, the more happy customers you're going to have. So it's important to get the search results tuned well. All right, we know we have distance. We know why we want to do it. How do we figure it out? Well, it turns out that it's not as straightforward as you might think. There are lots of formulas for finding distance. Four of the common ones we've got here are the rectangular distance. That's just your basic. If you assume the Earth is flat, and you remember this from high school geometry or algebra, you're just drawing, a line between 2 points on a plane. There's equirectangular projection, which sort of maps that onto a sphere a little bit. And then there's the real accurate formula, spherical log cosines and Haberstein. And it turns out, of course, that you can have fast or you can have accurate, but you don't necessarily get fast and accurate. Rectangular distance is the fastest one to compute, and the most accurate one is going to be the Haberstein. You're probably asking yourself, why are there these four methods? And the answer is that the Earth is not flat, and the Earth is not even spherical. So we have various ways of trying to cope with that. And you can see here two different formulas. The first one is the rectangular distance. As I said, you may remember this from high school algebra, the difference between the x locations, the difference between the y locations. Square both of those and take the square root. It gives you the hypotenuse on the triangle. And down below, as you can see, this is the Haberstein formula. This is notably more complex, and as a consequence, it's quite a bit more accurate. So which one you choose? Well, let's look at the accuracy of those. How much difference does it make if you use the accurate formula versus the quick and dirty formula? If we're going from Fort Lauderdale, Florida to New Haven, Connecticut, you notice that's almost north-south. We only get a difference of 3% between the more accurate and the less accurate method. On the other hand, if we go east-west and a little further north, you can see there's actually a 66% difference between the two computational methods. So, that's something that more people would consider a significant issue than 3%. Just to look at it in detail a little bit, the Haberstein and log cosines are the same down to about a meter, so you can use those pretty much interchangeably for any sort of information you'll get out of GPS. The equirectangular is a much closer approximation, but faster than the other two, and the rectangular one is not so close. You can see about a 66% error rate. But how much does that matter? I mean, most of us look at 66% error rate and say, oh, that's terrible. I couldn't possibly use that. Well, let's take the office I used to work out of. That's what the map has on it. I happen to know the nearest pizza parlor is less than a mile away from there. I can get the most precise distance out of the Haberstein right there, at least if I'm a bird. The problem is that humans have this bad habit of wanting to follow roads. So most of your users are going to care how long it takes for me to get there or for the pizza to get to me. So any sort of distance, no matter how accurate it is in a straight line distance, is only an approximation anyway. So it turns out that if you're already approximating, you could probably use any of them acceptably. Now, I frequently get questions like, well, but Tom, which one should I use? And the answer is the usual, it depends. Depends on how important it is you have fast queries, how big your index size is. You're going to be doing these distance computations for every document that matches the search results. So if you have 10 million documents, that's 10 million computations. If you have 100 million, could be 100 million computations. So it really can matter. And of course, it depends a little bit on the accuracy needed. Now, hopefully none of you are going to be trying to land an airplane based on this. And for the rest, it's just a matter of, it's an approximation for your users' time to get there. If I had to pick something, I'd probably start with equirectangular projection. It's a good compromise in the middle. And then test it and see how it works for your users and your data. All right. Now that we have the basic ideas of the computations down, how would you compute distance in CloudSearch? Well, CloudSearch contains a feature called rank expressions. And rank expressions are used to run a computation for each document that you match. You could do rank expressions to invoke something like popularity of a document or rating of a restaurant or number of likes to include those in. And it turns out that since it's a nice general tool, rank expressions can also be used to include distance in the computation. And once you've got that distance, you can use that for sorting or, as we said, for combining with other factors like text relevance, number of likes, etc. So rank expressions are going to be the key for how we actually do this in CloudSearch. Now, there are two types of rank expressions in CloudSearch. There's the static ones, which are just based on values in your documents, like number of likes, popularity, etc. And then there's query time rank expressions, which are kind of cool, which allow you to pass in the whole formula each time. And this is very useful because you can then include parameters in that formula, like, say, the user's latitude and the user's longitude. And then you can run that through one of the distance formulas. So we'll use query time rank expressions in CloudSearch to actually implement distance. This, by the way, is all documented in the CloudSearch Developer's Guide if you want to look at it in more detail. Okay, so let's just say I'm going to stick with the simplest one for my illustrations here, just the rectangular distance or the Cartesian distance, because it's the only one that fits well on a PowerPoint slide. So rank expressions are kind of like writing JavaScript. It has the standard math functions you'd expect, the logarithmic, trigonometric functions, min, max, floor, etc. So we convert the distance formula into something that most of the programmers will be comfortable with. We get the square root of the power, the second power of the distance. Let me rephrase that. Take the distance of the latitude, square it. Take the distance of the longitude, square it, and take the square root. Right? So this formula here is the same as that formula over there. So that's how you would express it. In terms of actually passing this into CloudSearch, query time rank expressions are simply parameters on your HTTP request. So you define a rank expression by saying ampersand rank dash and give it a name equals, and you get your expression. And then you have, so a concrete example of that would be ampersand rank dash geo equals the formula we developed on the previous slide. Now that defines the rank expression, but it doesn't put it into action. So to make it actually be used, we then say ampersand rank equals law. All right, and a sort of sample URL here. You can see we have our query. We select our rank expression that we define right there. And here, 1, 2, 3, and 4, 5, 6 represent the user's latitude and longitude. All right, now as I said, as you get better and better at this, you'll want to include more factors. And so right here, I'm just combining text relevance and distance. Now, we have the minor issue that with relevance, a higher score is better. With distance, closer is better, so a lower score is better. So to make them go the same direction, I subtracted text relevance from 1,000, which is the maximum distance. Sorry. All right. So now the problem is that on that last slide, we actually combined, we just added them together, so we're sort of assuming 1 point in text relevance equals 1 unit in distance, and that's probably not going to be the case, so we'll need to multiply one or the other by some factor to make it balance out. And that, of course, is where the art comes in, because which is more important varies by your application. For example, if you assume your users are on foot, an amount of distance that matters is going to be very, very different from the amount of distance if your user is going to drive there. Right? So there's no standard formula you can use. You just have to do it for your application. So you need to take a first approximation, test it, adjust it, test it again until you get something that works for you. Now, fortunately, to aid you in this process, CloudSearch has a feature called the rank expression comparator. And this is used to run 2 queries, or actually run 1 query with 2 different scores so you can see the results side by side and see how things work. So this is just a snapshot of it. So we're doing a search for Francisco in my geographic database. We're showing 25 records per page. Over here we have the base that we're referencing. And over here I've changed one factor. I've changed the weighting for the name field. And what you can see is we've got different results here. The green arrow means this result went up compared to the reference one. This one went down from its previous position. And these two weren't in the top 25 at all the first time, so they got added to the result set. So you can just look at your data here, make a change, and say, oh, that looks better, or oh, that looks worse, I better back that change out. So you can change the weight. You can add things like, you know, the logarithm of the number of likes or anything else just by typing it in the field up here. And as you make each change, you immediately see the search results. And it makes it very, very rapid for going through this process to get to a good approximation for how to weight distance. If you're just sorting by distance, you don't have to deal with this at all. You just say sort equals geo and or rank equals geo, and you're there. But once you start combining the factors, this tool becomes your friend. Okay, now we know how to do the computation. How do we get the data in there? So CloudSearch currently only supports unsigned integers. That's a bit of a problem for us because the latitude ranges from -90 to 90 degrees, and the longitude goes from -180 to 180. So we have to convert those to positive ranges. And then because those are floating point numbers and we're going to want some decimal places, we're going to multiply them by 1,000. So the number that you store for latitude in your index will be the original latitude plus 90 degrees times 1,000, for example. Multiplier depends on what resolution you need there. Now, this actually performs fairly well. CloudSearch can do like 10 million. Oh, sorry. I'm just hearing that I didn't get an advance on the slides there. Okay, good. All right. So performance. You can do 10 million a second, but what if you got 100 million documents? Well, you probably don't want your user waiting for 10 seconds. But realistically, if I'm in San Francisco and I'm searching for a restaurant, you probably know that I'm not going to Tokyo for dinner. So we can restrict our search results to say only the state of California, or only like the zip code, or a range of the latitude and longitude. All of those will tend to cut down the number of computations that have to be done. Obviously, there's probably only several hundred restaurants in San Francisco as opposed to several million in the world. And several hundred go so fast that you hardly notice the computation time at all. Here's a fairly complex set of data, but I want you to look at the red column mostly. These are the amount of times it takes to do a distance query. This was run over something that has 8 million documents in it, and the simplest distance formula takes a second and a half, 1,560 milliseconds, to run over 8 million documents. That's a little slow for a lot of applications, and you can see the Haversine takes twice that. But if I put a restriction on it, and this restriction was plus or minus 100 miles, I get about 400 or 4,000 restaurants, 3,800, and you can see those take about 900 milliseconds to run. And it turns out, due to CloudSearch's architecture, it's slightly faster if I use a literal field for a restriction. And here, then, I was able to actually run these queries in, 50 to 100 milliseconds, which is faster for most applications, fast enough for most applications. So you can see we're looking at a difference between 1,500 and 5% of that. So don't search the entire world when you're doing these things. Put a restriction on it. As I said, you could restrict it to, the state, the district that they're in, a few nearby zip codes, or latitude and longitude range, and that will speed things up considerably. All right, let's look at a demo application that I built based on CloudSearch in this. So here's just a screenshot, but I'm going to flip out to the application itself. So this is just a simple mapping application. Again, this was the GeoNames database. It has 8 million points around the world in it. And I'm using Google Maps to display the results. You can see as I move things around, it updates things. I've got the standard sort of search results here. Over here, I've got CloudSearch, so I can facet. So notice all of a sudden I'm only in Canada, or only show results from Mexico. So we can facet, we can search, we can combine this with distance. Now what I have here is a little slider. Remember I was talking about wanting to combine distance with other factors like text relevance. So if I go for text relevance, things get spread out all over the map. If I move the slider all the way over to distance, wham, you'll notice it's all right near the center of the map. Usually what you want is some combination of the two. that combines text relevance with some sort of distance factor. And this allows you to see the effect of that in real time. So this is the kind of application you might build for visualizing your code, or sorry, for visualizing your data, letting users see where it is. And of course, we can drill down to wherever the users happen to be. So if I was looking for something near my office, there we go. I'm right around here. All right, so that's a demo application. Dropping back to PowerPoint. This demo application is actually very, very simple. It's got an HTML page with JavaScript on it, and that actually has pretty much the entire application. Due to security restrictions in the browser, the HTML page can only talk back to the server that served that page. So I've got a Tomcat server in the middle that all it does is forward the request to CloudSearch. So, and then we have CloudSearch. The JavaScript just uses jQuery and AJAX and the Google Maps API to do all of that. And the Tomcat server is just in Java, and it's just for forwarding requests. So this is a very simple architecture. Backing up for a moment, in a more typical application, you'd have your typical middle tier web application here doing more coordination, etc. But for a demo, it's nice to have just everything on the HTML page. And here's what it looks like to actual query CloudSearch. So this is just an AJAX call using jQuery. And all you really have to do is pass in the search URL, the query that you want to execute, the name of your search domain, the fields you want to get back, and then here's where we define the rank expression. We name it geo, and here we have math.square-root, math.power, math.abyss. Here we have the most important thing, which is the user's latitude and the user's longitude dropped into the simple rectangular distance formula. And then we have the data type we want to get back, and this is the function that gets called when the call succeeds. It gets our hit section of it, we display our search results, and then we populate the map, and we're done. So it's a fairly straightforward process to get it up and running. Now, most of you probably have latitude and longitude for your data. You know if you have a list of restaurants where they are, etc. But many times also you don't. So if you don't know latitude and longitude, I see. Sorry, sometimes the slide doesn't update, so let me just do that again. There we go. All right, so if you don't know the latitude and longitude, there are a number of services that do what we call geocoding, which is taking an address and mapping it to a latitude and longitude pair. There are lots of services. If you just Google geocoding services, you'll get a list of them. Many of them have free tiers, although most of the free tiers have restrictions, like you can do 1,000 lookups a day or something like that. Frequently, if your database isn't huge, the free tier is enough if you run it over the course of a week or so to tag all of your data with its location and keep up. But if you have higher requirements, I think almost all of these have a paid tier as well. So you can do whatever it is that you need to do. So if you don't have the latitude and longitude data, you can get it from a geocoding service. All right, so we're coming up to the end here. So what we've talked about, local search. Almost all applications these days have some local search associated with them for some reason. So you want to be aware of that, design that into your applications. CloudSearch allows you to incorporate local information into your search, and it allows you to not only sort things by distance, but to combine it together with other factors like rating and likes to give your users the best search results. And those search results quality search results drive users to your site, and they increase sales. So it's important to have that local component in your search. And of course, we mentioned at the end, geocoding services are available if you need them. Let's see, resources, not done yet, but I got the data for my demo from geonames.org. And we'll have the slides on SlideShare soon. If you're interested in the sample code, we haven't formally released that yet, but I'm going through that process. Drop me an email if you'd like to take a look at it. And the computations I based it on, there's this nice little blog entry there that talks about all of the computations, or you can look at the ones on Wikipedia. So let's see, Mike, do we have some questions? Oh yes, if you have any questions, please type them into the box. Okay, a moment. Let's see, okay. I got a question about range filters. So you could filter on a range based on a literal value, like you can say state equals California or zip equals 94402, or you can do a numeric range if you want to do a range on your latitude and longitude. In CloudSearch, the literal ranges are applied earlier in the pipeline and produce slightly better performance on this, but either one is much, much better than doing 10 million computations when you only have to do 1,000. Okay. Let's see. So, sorry, I should reread the question. So I said you provided an example based on the rectangular distance calculation. Could you please provide an example expression based on the other formulas so we can easily compare them without having to work out the expressions from the formulas first? Let me just see if I can. So I can definitely send them to you if you drop me an email. I have them in various forms here, but I wasn't set up to show them right now. So why don't you drop me an email at tomhill@amazon.com, and I will send you back Java forms or JavaScript forms of those equations. If you want to do a bounding box query, is that just a range query like you showed with BQ equals lower bound dot dot upper bound on the and long fields? And the answer is yes. So yeah, that's exactly what you would do. So if you want to do a range query on the latitude and longitude, it would be BQ, equals longitude colon lower bound, upper bound. You'd have to specify which field you're querying on. Once you push documents to CloudSearch, how fast will it index and when can you begin querying? CloudSearch, we usually say it's seconds to minutes, so it depends on how much data you're pushing, but it's there quickly. You can start searching and it'll start immediately, but it'll start showing up, in a few seconds, which is more typical. Typically, 10 to 30 seconds, but it can take longer depending on load, etc. Let's see, can CloudSearch be used for big data? Depends on your definition of big data. So, yes, so up to terabytes. We're not up to petabytes yet. But yes, you can definitely do some interesting big data things with CloudSearch. All right. And yeah, you can also combine CloudSearch with Dynamo to process really large amounts of data in Dynamo and then extract the text and move it over to CloudSearch to use the two in combination, so you get good search results coupled with the massive data quality handling of Dynamo. Oh, okay. Sorry, I had a couple more. It says, when should I look for things in zip code or city versus within a radius? I would always try to go with the restriction for a city or a zip code first, just because that's going to perform better than the computations you need to restrict to a range. So I would always say narrow it down to California or Boston or, Texas, whatever, to narrow things down. And then if you want to, you can also do a numeric restriction like a zip code range. But I would always start with the literal restriction just to chunk your data down to a smaller section. Let's see. I had a question about using Cartesian tiers, and yes, you could implement them on CloudSearch, but it'd be mostly on you. So it's just a set of Boolean queries, basically. You'll index the data that you need to do the Cartesian tiers, and then you can implement them. For those that are wondering what I'm talking about, Cartesian tiers is just another way of implementing approximation of distance filtering on a search engine. So it's just a mathematical thing you can do. Suppose I want to locate a restaurant in Australia. How can I get an accurate location since longitude and latitude are being used for travel purposes and not business? I'm not quite following that. So So you should be able to get an accurate latitude and longitude from them by using one of the geocoding services. So you just type the location into the geocoding service. It would give you back a latitude and longitude. You'd include that in your document in CloudSearch, and then you'd use the user's location, which you get from their phone or from their browser. All modern browsers support geolocation. So you would be able to do that very easily for a restaurant in Australia. We've got the question of, will geospatial functions be built into CloudSearch in the future? We are definitely looking into doing that. I can't make commitments about unreleased features at the moment, but that would be a very obvious thing to do. So, question about what is the performance difference of literal ranges versus numeric data? And to answer that one, I'm going to just pop back here. As you can see, these are the numeric ranges. These are the literal ranges. So the literals generally perform a little bit better, so I encourage you to use literal restrictions. You can also use both of them at the same time. And for performance reasons, do I recommend using literal data for storing lat long within the index? If you're going to do numeric ranges across it, then it has to be numeric. If you're going to say map things to whole degrees or tenths of degrees, then you could use the literal types. But bear in mind, you could use, as I said, you can use a literal and a numeric filter. So you could say, I'm going to approximate San Francisco by saying plus or minus 1 degree, and then I could use the lat long as a numeric type if I wanted to apply a range to that to restrict things a little bit more. All right, I think we've got all of them there. So I'd like to thank you all very much for coming. I'd like to reiterate that we will have these slides will be on SlideShare, and we will be sending you a link to that. And YouTube, the recording will be on the YouTube channel. And thank you all very much for coming. And feel free to contact me, Tom Hill at Amazon.com, if you have any questions. Thank you all very much. Thanks for coming.